Electrons and matter waves. In this video, we will see the dual nature of light and matter, or in plain English, if the light exhibits both a particle and a wave nature, then all matter has both a particle and a wave nature. By the way, if you like this video, don't forget to like and subscribe to this channel and activate the bell. It's very important for the continuity of this channel. Let us start with the de Broglie's hypothesis. In 1924, the French physicist Louis de Broglie postulated that because photons have wave and particle characteristics, perhaps all forms of matter have wave as well as particle properties. Let us look at the de Broglie's idea in more detail. The relationship between energy and momentum for a photon is P equals energy divided by speed of light. The energy for this photon is E equals Planck constant times frequency, and the speed of this photon is C equals lambda times frequency. Then we can combine these three equations to obtain that the photon wavelength is Planck constant divided by its momentum. The de Broglie's revolutionary idea was that the wavelength of a material particle would be related to its momentum in the same way as for a photon. In short, de Broglie suggested that for all free particles with rest mass m having linear momentum p, the wavelength is given by Let's see how it works. Determine the wavelength of an electron that has been accelerated through a potential difference of 50 volts. The potential energy is charge times potential difference. We now apply conservation of energy. The gain in kinetic energy equals the loss in potential energy. So the electron's speed is given as follows. The formula, the de Broglie wavelength of a particle, is valid classically and relativistically. But since the electron's speed is much less than the speed of light, so relativity is not needed. After finding V, we find the de Broglie wavelength. If electrons can behave like waves, then they can be diffracted in the same way as waves. Let's now remember a little bit how waves diffract. Diffraction is the spreading out of waves as they pass through an aperture or around objects. It occurs when the size of the aperture or obstacle is of the same order of magnitude as the wavelength of the incident wave. This is shown in the diagram below. The wave that passed through the slits was diffracted and will interfere with itself. Interference can be either constructive or destructive. When interference is constructive, the intensity of the wave will increase. When interference is destructive, the intensity will decrease, sometimes to a point where it is completely destroyed. The de Broglie's proposal was made at a time when there was no direct experimental evidence that particles have wave characteristics. But in 1927, two physicists, Davison and Garmer, performed an experiment in which electrons leave the filament F and are accelerated by voltage V. The beam strikes a crystal and the scattered beam is detected at an angle phi relative to the incident beam. The regular array of atoms in a crystal can act as a diffraction grating for electrons. Atoms in a surface plane are arranged in rows with a distance d between its slits. The experiment employed low-energy electrons which do not penetrate the crystal. The diffraction of the electrons was caused by the nickel atoms in the surface of the crystal. A beam of electrons with an energy of 54 electron volts was directed at right angles to a surface of a nickel crystal with distance equals 2.15 nanometers. Electrons are reflected back, but an intense, sharp reflected beam was observed at an angle of 50 degrees with respect to the incident beam. Treating the electrons as waves, we need to determine the condition where the difference in path traveled by the wave diffracted from adjacent atoms in an integer multiple of the de Broglie wavelength, so that constructive interference occurs. The path length difference is d times sine of 50 degrees. This path difference is one wavelength of the electron, and Davison and Germer calculated this wavelength. We can compare this value with that expected on the basis of the de Broglie theory. This is in excellent agreement with the value found from the diffraction maximum and provides strong evidence in favor of the de Broglie theory. We now compare the wavelength of elementary particles such as neutrons with the wavelength of ordinary objects such as a ball. Pay attention. This problem is a matter of substitution into the equation for the de Broglie wavelength. The de Broglie wavelength of a neutron is of the order of atomic dimensions, and the spacing between atoms in a solid and neutron diffraction is a useful tool to identify atomic structures. So this neutron will appear wave-like. We repeat the calculation with the baseball data. We can see that the ball, by contrast, have very small wavelength. The properties of waves, such as interference and diffraction, are significant only when the size of object or slit is not much larger than the wavelength. The ball has a wavelength much smaller than any object or slit through which the ball could possibly pass, so we cannot see the wave properties of a ball. This explains why all macroscopic objects appear particle-like. Wave-particle duality, the principle of complementarity. The experiments such as photoelectric effect, the Compton effect, and other experiments have placed the particle theory of light on a firm experimental basis. The experiments such as Young's double-slit experiment, the polarization of light, and others put the wave theory of light on a firm footing. We have just seen that electrons and any objects behave as waves or particles. We seem to be in a dilemma. Light and electrons never behave simultaneously as if they consist of both particles and waves. In each specific experiment, they behave either as particles or as waves, but never as both. Apparently, light and electrons are a more complex phenomenon than just a simple wave or a simple beam of particles. We must recognize that the two aspects of light and electrons are different phases, that light and electrons show to experimenters. This suggested to the great Danish physicist Niels Bohr that the particle and wave descriptions of light and of matter are both necessary, even though they are logically incompatible with each other. They must be regarded as being complementary to each other. This led Bohr to formulate what is called the Principle of Complementarity. The wave and particle models are both required for a complete description of matter and of electromagnetic radiation. Since these two models are mutually exclusive, they cannot be used simultaneously. Each experiment, or the experimenter who designs the experiment, selects one or the other description as the proper description for that experiment.